What I want to talk about today is a few advanced features. The last time we were talking about access control. Now, one of the things to remember is that you basically have inheritance. So basically, you are all given a user that when you connect to the database, you have a certain user. In addition to your login user, you may actually be given access to different roles. So you can actually inherit all the access rights given to those roles. And generally, when you're operating as first the login user and then the other roles, but you can switch to a specific role that you have given access to. And it kind of, it gets a little bit more interesting because you actually can also have roles that can inherit or not inherit the privileges. So for example, the role Joe can inherit privileges. So for example, I have given admin to Joe. So since Joe can inherit, Joe user, the role Joe, can actually do everything that admin does, because the Joe itself can inherit from other roles. I create another role called Will that does not inherit, and admin does not inherit. So if I grant Will to admin, that means that even though admin has access right to Will, when your role is set to Will, you don't actually inherit. But when you're set to admin, you don't actually inherit what Will does. Only if you explicitly set the Will, then you inherit it. In the same way, Joe will not inherit from Will because that there is no inherit for admin. So even though Joe has admin and Joe has Will, Joe does not inherit from Will because admin does not inherit from that. Is this crazy complicated? But I just want you to know that there is a whole access control methodology, and there's actually a class on this that goes into much more detail, taught by David Spooner. So access control is a little bit more interesting because you can discuss whether you can inherit from other rights that are given to you, even though when you are not explicitly set to be operating as one, or whether you have the explicitly set to those roles. And then those roles themselves can have access rights that they can give to other people or not. So there's a whole hierarchy as such. This is all on the course notes, but I wanted to kind of put that out there. And you will have a slightly different implementation depending on where you end up using it. Okay, so now we talked about the system tables last time. So now I'm going to basically, this is the same type of thing that you learn in any programming language. When you teach, I teach you the hardest possible way of doing something, then you see that there's all sorts of ways that your life could have been easier. We do that because it builds character, right? Because if you do the hard way and you learn how to think like the language, then you use these advanced constructs only when you think that there is no other way to do it. So one of the things that really is very annoying when you write SQL is that you don't have if statements, right? Sometimes you want to return something in the select. If the value is something, return A, otherwise return B. But you actually do have an if statement that you can put. This is not standard. It's slightly different in Oracle or other languages, but it exists in every single one of them. So you can actually have a little if statement that says that for each attribute A that you return a new attribute, and this attribute is going to have conditional values. If the value of A1 is 1, then you're going to return 1. If it is 2, you're going to return string 2, and otherwise you're going to return other, and then the case has to have an end, right? So you basically created a new column on the fly using conditions, and then you have this. You don't actually need it like this, right? You can write this without the case statement. You basically need to have three SQL statements and union them, right? You need one for where A is equal to 1 for where A is equal to 2, one for where A is not 1 or 2, and then you union them, you will get the same exact result. This just simplifies your life. Yes?
Is one faster than the other, or
are they the same? You would expect that this is most likely faster, okay? But I've had this conversation with others in my office hours too. One thing about Postgres especially is that Postgres is very efficient with unions. And so there is no necessarily big performance penalty, but much more likely this is faster, right? But also think about the following, right? So if you're writing a real application, having these may be useful, but ultimately it's going to be very complex queries that are hard to edit. What would I do instead of doing this is I already showed you how to write a procedure. I would write a procedure to return this and just call that function, right? So that would be the same result. So I've already given you the power of procedure, right? So you can do all of this stuff anyway. But here it goes. It's here. Okay. Now there's some kind of more fun stuff. So the group by, we just group by one thing and then looked at it. But you can group by a whole bunch of things. So there's actually a database for this online, I believe. Right, so this is the database. I guess LaTeX does not bring that. So, so this is the group by. It basically creates a database of events. So okay. I basically was not very inspired at 2 a.m. at night. So, so my events are not so exciting. But regardless, so generally you want to, let's say that you want to group by, some aspect, like you want to group by the day, and then aggregate. You can count how many different times there are. You can add up the prices and stuff like that. So you can write, for example, select from events, group by day, and then in that case you can return a day, and then you can return the number of tuples, and then you can return, let's say, the sum of price. Okay, so this is what we have learned. You can also do the same kind of thing, but now instead of this, you can actually group by time and return time. And this is what you get. And you can simply do no group by, right? So instead of this, you can actually simply return the count of everything in the database. So basically, sometimes maybe you wanted to take your data and slice and dice in every possible way, and then from this one, check for certain things, right? So in that case, you can compute all of these group bys at the same time. Instead of writing all this, you have to say that I am going to actually group by first by time, then by day, and then by everything. Okay, making sure I'm doing this right. Okay, so, and I'm going to actually return day and time and this. So this kind of makes life a little bit more interesting, because if you group by time, then you should not be returning day, right? Because that's what we were just doing. But the syntax is going to basically allow it and handle all that for you. Let's see, what did I do wrong? Grouping, group by grouping set, so I need a comma. Okay. So now it basically did all those three queries and then took a union. But of course, for some queries, for example, the day did not exist because if you group by time, you have aggregated over all the days, right? And then for 12 o'clock, there were two for 2, and 4 for 1. Then you took a group by of time, so you don't have time, but you have the group by day, so you don't have time, but you have these two. And then you group by everything, so you don't have both of these, but then you have the same value. So this is exactly the same results we just got, right? So this was group by everything, this is group by time, and this is group by day, but all of them together. There's a thing called Rollup. Okay, so let's see if I'm going to be able to write this. So what the rollup will do is it will actually compute more and more aggregation. So aggregating over aggregation. So first you group by time and day together. Next you're going to group by only time. Then you're going to group by with nothing. So find everything, all the constraints for the same way. So, okay. So you group by day and time, right? So for Monday at 12, Wednesday at 12, Wednesday at 2. Then you group by only time, right, for 12 o'clock. So 12 o'clock there's 2 things, 2 o'clock there is 2 things, and 4 o'clock there is 1 thing. Then you group by everything, then you will only get this. So if I were to do the reverse, then it will group by, the first group by will be the same, but then it's going to group by first day and time, then by day, right? So day and time, then just day and time, just day, and everything. So these are queries people often use in data warehousing applications where you really need to know everything you want about the state table. So you don't want to group by one thing, you want to find all possible groupings, and then you probably will find things in this, if you have something interesting going on for a certain grouping, then you can ask. There is one more version of this, which is called the cube. It sounds like, I think there was a horrible sci-fi movie called The Cube. Have you ever seen that? People get dice and so on.
I think there was a sequel.
That's true, Cube 2. I do know a lot about such things, sadly. All right, so what Cube will do is it will do every possible subset of these attributes. So it will basically do day and time, group by day and time, group by day, group by time, and group by nothing, right? So you have group by day and time, and just day, group by day and time, just day, then group by time only, and group by everything. Okay. So one more variation. You can also compute an aggregate. Let's say you wanted to find the aggregate for day, but then add it to this table. So basically you want to find the aggregate of all Mondays, and then add it here. So it will be something like you have select day time price, but I want to compute also the sum of price partition over day. So I have to look up the syntax. Over partition by day. All right. Over partition by day. Okay. This is a totally different version because this is not actually like a group by. because with a group by, you actually group and then return a tuple for each group. Here, you really return all the tuples, but then you compute an aggregate over the tuples that are going to be returned by summing the price for all the ones for the same day. And just to show you what that looks like, I'm going to order by day. Right? So basically, for example, all the events that are on Monday, if you add up the events on Monday, you will find this add up to 39. So now I added that as a window operation over this tuples based on a partition over day. And these two, if you partition over a day, the Wednesdays have the total price 18, so they will both have 18. Okay? So these are the types of things you will have to learn when you're actually trying to do some more complex, they call data warehousing operations, where you really take the data and analyze all possible aggregations over it and then ask questions of what they are. And there are efficient implementations of these. So with that, let's do recursion. Oh man. All right, so the recursion, because I know that you all love recursion and you love Prolog. Yeah, I hear that a lot. So you can write recursive queries in SQL too, and a lot of databases implement that. Or Oracle, I'm not sure if they do, but for sure IBM DB2 does. And I don't know if SQL Server does, but most likely. Now, okay, recursion is not only for torturing CS students, okay, or Prolog. So recursion is also very useful for some basic applications, like suppose you have a thread, right? So this is the most common thing that you use every day, right? Assuming that you still actually use Facebook stuff, or like, let's say, Reddit. Everything in Reddit is organized as a thread, right? So you have a message, you have a response to that message, a response to that message. If you were to store that information in a database, you cannot store it as a thread. You will actually take the thread and you would distribute it to be, I'm losing connection here. You can distribute it to be basically pairs of tuples, right? A is a response to B, C is a response to A, D is a response to C. So basically what you need to do then is take those paths, and then you want to traverse those paths by continuously joining with itself. In essence, what we did for degree of Kevin Bacon, what we did for the quiz is an instance of that. But you want to do this as long as you have paths to explore. So to be able to do that, you would write a recursive query, and you have to be very careful, because if you don't write good recursion, A, it may not terminate. B, it may be very inefficient because you are recomputing the same thing over and over, right? Left recursion versus right recursion. Those of you who are in ProGlang, there's a use for all of that. All right, so what we are going to do is we are going to use a different database called family relations, and all of these are linked from the course website, right? So, so you have, I tried to find the most cookie names. So you have Dakota is the parent of Madison. Madison is the parent of Ava and Sophia. Sophia is the parent of Noah. Noah is the parent of Emma. Right? So if you want the ancestor relations, that Dakota is the ancestor of Ava through Madison, and Dakota is the ancestor of Noah, and as well as Emma. Right? So you can kind of go through the whole recursion, right? So what we want to do is create a grand ancestor relation of who is an ancestor of who. So this is a Postgres syntax that you can use for non-recursive queries too, but I will show you how to do the recursion. So we are going to say with recursive ancestor let's call this A and C, or parent-child S. So I'm going to create first a relation called ancestor with two attributes, parent and child, but I'm going to also put degree here. Okay, and I need to make sure that I'm doing this correctly. All right, I think I am. So first I'm going to define what this relation is using SQL. Then I'm going to write an SQL to query from it. So like, this is like having the query in the from statement. It's just that you have it before the from statement, but it serves the same purpose. So we are going to write basic recursion, right? So what is the, zero ancestor relation? Somebody is the parent is, if A is parent of B, then A is ancestor of B, right? So what we can do is we can have select as parent-child from parents, and I'm going to return 1 as degree. Okay? So anybody in the parents relation is an ancestor, parent, and child, right? Then I am going to do the recursion. So with the recursion, you always want to use union all, which is what they told me. But so to find other ancestors, I am going to look at parents P and ancestors, I'm going to call this as ancestors A. So this is why it's recursive, because while I'm trying to define what ancestor is, I'm actually joining with ancestors to find what it is, right? But I have a basis. There's always a basis statement, which is the first one. First, everybody who's parent-child that's already in the table is an ancestor. And take that, union that with parents again, such that p.child is equal to a.parent, and return p.parent, a.child, and a.degree plus 1. Okay. Does that seem correct? So your parent, child, so that's an ancestor of that person. Okay. So now what I can do is, we don't have that, I am going to return select star from ancestors. So here, if you wanted to take this table and join with something else, you can. If you want to do a selection over this, you can. So for example, you only want to return ancestors with degree greater than 1. And I have no proof that this is going to work. Let's hope for the best. All right, it did finish. All right, does that look correct? So Dakota is the parent of Emma at degree 4, right? So Dakota to medicine, medicine to Sophia, Sophia to no, to Emma. So that's correct. Okay. So remember that this is kind of the easy way to see, but this is something you really have to do when you're really working with transitive relations that you need to query. Then you need some sort of recursion. To do the same thing, Oracle has a specific statement called connect by. So the connect by is very limiting. It's only for doing this traversal, whereas recursion is very general. You can do many different types of things with recursion. Any questions? Now, incidentally, you can use this with statement for any query. So instead of really putting a statement in hey, instead of putting a anonymous query in the from statement, you can really define a query here in the with statement and then select from it. And I actually did not know that at first. When I thought that, when I was doing something, somebody in one of my database classes showed me, this is how you do this. And I said, well, I don't want to teach people how, things that are not SQL standard. And then he actually found the SQL standard and showed me that is actually SQL standard. So, so you are all going to show me things that I don't know. But the with statement is actually an SQL standard. It's actually a more natural way of defining a relation or an anonymous view, and then using that in the next query. Okay. All right. So that is all on basic SQL. That basically all the different things that you can do that go a little beyond what we have seen, but are super useful. Will I ever ask you to do recursion in an exam? I don't think so. But I think that it's really useful for you to learn. But even more cool is that Postgres actually is so basically the first part of this class, I told you that you cannot do lots of things. The first thing that we discussed, the first class was relational data model has this rule that every value has to be a single value, right? So you cannot have records, you cannot have sets of values, because all of these violate relational data model. And the reason for that is very simple. The simpler your data model is, the easier it is to modify, and easier to see what it does. So the databases are optimized for doing certain things. So, all this SQL query optimization is written assuming that your data is flat. And for the most part, you should really use it as such, except for some things that we're going to talk about now. So, the news for you is that Postgres is actually object-oriented and highly typed. And you can use complex data types, and you can create complex data types. And it is fully extensible, and in fact, it's an amazing software engineering feat. Okay? When you learn about software engineering, you start to realize Postgres is an amazing piece of software. So you can do all sorts of things in Postgres that will basically totally violate all the rules that I taught you not to use in the beginning of this class. Let's start with simple ones. You can create complex data types that basically allow you to actually have records of data. So you can say something like create type, let's call that font type, that has a number as, let's say, this, and type as another character string. Okay. So I have created a new data type which has two parts in itself. There is a number and a type. Now I'm going to create a table called, let's say, a person that has an ID, name, and a font, which is of font type. I know that you feel cheated because this is exactly what I told you should not do. Well, let's try and see what that does. Font type does not exist. What did I do wrong with font type? Create type, font type. All right. Apparently num is a keyword.
Any types of keyword?
Should be fine. All right, let's see. I've done all this last night, so we'll take a look. Oh, I forgot that. Oh, S. Okay. Okay. So if you were to look at person, that it has a new type, font type, but this is not a simple type anymore because it has two parts. It has a number and a type. So if I want to insert into this, so if I want to insert into person values, all right, I finally learned her name. So I'm actually going to insert a font that requires a number and a type. Let's call it work. And I'm going to declare this as a font type. So there are many versions of this. Everyone is a slightly different syntax, so let's see if this is the one that works. All right, that works. All right, so you have seen that you can cast something as a new type. So the typecasting, explicit typecasting is possible. So what I'm doing is I'm taking this row of values, I'm casting it this type. So if I were to say, for example, select star from person, that the font is actually now a complex value. If I wanted to actually select from this, I would have to say, for example, font dot type is equal to work, right? So if I want to return this, it will say, return me this. Now the problem is that this fails. And if you think just a little bit, you will see why, because according to SQL syntax, whenever you have x.y, this is the name of a table, or an alias for a table, right? So it's not allowed because that's actually not valid. So all you need to do is, instead of this, just put it in a parenthesis so it understands that's what you're trying to do. That is just a little way around data type like this. Okay? So you can, in fact, have complex data types. In fact, wait, there's even more. For 1999, all right, so you can actually create arrays of values. So you can create but just because you can doesn't mean you should. So I'm going to create a table called messages that has one attribute called ID, and the message itself is actually an array of text, right? So you can actually create an array of values, okay? Now let's try to insert into this one. Okay, let's see if I can remember how to do this. So we are going into a universe that is starting to look more and more like Python. So now the message itself is an array of text values that has, it starts actually at 1, not at 0, 1, 2, 3, 4, 5. So you can ask things like select message of 1 from an ID from messages. Or you can have message of 2. Right? So you can take values, you can wrap them in a collection, you can push that into a data type, you can take the values and you can access individual pieces of it. So you actually can do all of the things that I told you not to do. Okay? So you can have collections and you can have records of things. So The reason for doing a lot of these things is actually to, let's see if there's anything else. Oh, you can do slicing. That was why I was excited. Okay, so you can actually slice like in Python. It's just like the world has given me a gift. So you can slice. It feels like it's Python and makes me happy. All right, so you can do all sorts of things. But the reason for doing all of this is not that you now should use all this complex stuff. It is that these are used to create very specific potential data types that are useful. Okay, so let me give you a few examples of those. First of all, you can do JSON. JSON is a data type that is supported by Postgres. So you can create JSON objects, and then you can access different pieces of it. I did not really learn too much about how you do JSON, because I spent, like all of last semester doing JSON. But you can convert to and from JSON using Postgres queries, which is okay. But really, the more interesting stuff is these two that I want to talk about. That there are extensions of Postgres for doing specific things. So when you're doing actually, let's say, geographic data, when you're dealing with geographic data, it does make sense that you say that two things are part of the same object. Like, for example, you have for any business location an X and a Y value, right? So X and Y value together actually make up a point that is a single object, and you can take 2 points and find the distance between them, or you can take 2 points, or you can take a point and a polygon and find that that point is inside that polygon. Okay? So all of that is possible only if you have typed objects. These typed objects are supported by extensions. Some of these extensions are standard that comes with Postgres. Some of them are things that you have to install. And for geographic data, the extension is called PostGIS. PostGIS used to be very hard to install, and I didn't even try to do it on the database server that we have, just because I don't want to mess things up there. But if you have your own, you can try it. So on the Mac, it is just simply clicking in a button when you install Postgres, whether it asks you whether you want to install PostGIS. Once you install PostGIS, the one thing you have to do is you actually have to create an extension called PostGIS explicitly. And what it will do is it will create a special template database called template PostGIS that actually has all the functions and data types already defined. So they are not part of databases that were already created, bless you, but you can create one for a new database. So what you would end up doing is you can create a new database with this given template, which is what I did. So if I were to connect to GeoDB, it basically has all of these tables and views that basically come with PostGIS that are preloaded. So what are all of these different data tables and definitions are for? So one of the things that comes with PostGIS is a whole projection system of taking the sphere of the world and then projecting it to a Latin long, right? Because to find the distance between 2 points, you have to know what the projection that was used to do it is, right? Have you ever taken a geology class here? I'm sure you if you do, that they mention all of that stuff. So I am not an expert in that, but this is an important part of doing things. And this is kind of the technology that runs a lot of things that you use every day and take for granted, right? Now, whenever you write a query, you get distance from one point to everything, right? It's always ordered by distance. When you use Google Maps, right? Maps are organized in basically adjacency, so you can go to the left and to the right and retrieve the next thing. All of that is possible because you have these advanced data types that understand things that are geographic, that are adjacent to each other, that is one is inside the other, that you can have distance. You can store road segments, so you can understand the shortest distance between two things based on roads. You can understand that something is inside an area because you have polygons stored for all of the different regions. This is the whole thing that makes it possible. Now, I'm not saying that it's all Postgres, but this is within your view. So here's an example that we can do. So, for example, I'm going to create a table called business with location. And the location is going to be a geography that is a point data type with this projection. So this is the projection that is used to store the points. So 4326 is generally the common one. Okay. So the location itself is a geography data type that stores a single point. In the same way I showed you collections, you could actually be storing an array of points, which is what a polygon is, because you basically trace the points in the polygon. So let's do these two. Hopefully this will work. Okay. So this is basically the syntax for this. So it doesn't really work the same way because PostGIS is kind of an older implementation, but you basically give a point, a let long value, and you give the SRID, which was this projection system that we use. And given this text, you can create a geography and then store it in this tuple. So these are the actual locations. Okay, so the location is stored as some binary representation of the point value, but I believe that you can actually use st of x of location. No? Okay. I can never remember these functions. All right. I have to look it up every single time. I think there's an st of x. There is, in fact, one called st_distance that will find the distance between any two locations. But this is this is a Cartesian distance. It's not going through some certain roads, but you can also have that. So you can, for example, say that from b with loc, join it with itself, where b1 dot name is not the same as b2 dot name. And in fact, I'm going to use less than. And then I'm going to find the distance. And I'm going to order by distance ascending. So this is called a spatial join. I'm basically finding two things and then their distance with respect to each other. And this is the same kind of thing you wrote in like homework 3, right? Okay. And the distance here is in terms of meters, because it's metric. So if you wanted to really do it in terms of kilometers, you can divide by 1,000. You can cast it as a numerical value so that it's a little more pleasant. And so on and so forth. So this is true, right? Shalimar is closer to RPI than Placid Baker, but it doesn't really go through any kind of roads to do this. Okay? So there is a whole slew of things in here, and we are going to go back and talk about some of the indices when we talk about indexing, because it's also very cool. But the other thing that you can do is you can treat text a little bit more special. So anytime we had a bunch of text, like when you had Yelp, right? You had the Yelp reviews. Reviews is like this huge piece of text. Anytime you said, okay, try to find whether it contains a certain keyword, you take the text, and then you find whether that text contains a certain word. But that's not really at all what you do, for example, when you type a keyword to Google. Google doesn't just return you any document that contains that keyword. Okay? There is a whole bunch of other things that go into the Google ranking. Put that aside. But it also looks at if that word appears many times in the document, then it's more relevant to your query than the one that appears only once. Right? So this kind of text processing requires that you take the text and find individual words in the text, make them into tokens, tokenize the whole thing, and then count those tokens to find compute relevance. So there's a whole part of computer science called information retrieval that looks at probabilistic or different models for doing that. There's, deep, deep theory. But the nice thing is that that comes standard with Postgres, that you can do text queries very easily. So I will show you one or two. So let's first look at this one. So TS is the text area. So for example, what it will do is, if you give it a text like this, it will convert it to a vector. So what that vector does is, it takes every single word in it and finds how many times it occurs and the location, right? So 8 occurs in location 3, 1, 2, 3. Fat occurs in location 1 and 4. This is the vector representation of this specific text. Okay? So in information retrieval, you generally find something's relevance by looking at two vectors and then doing a cosine between them, linear algebra, multivariable calculus. Okay? You can do things like take a Boolean query like this. Now the Boolean query says, look at this keyword, and this keyword, all of them occurring in the document. But it's going to say, well, this query is great, except that the word the is not really relevant at all because almost everything will have that. So it's called a stop word, so I'm going to remove it. It already comes, preloaded with that type of thing. Okay? And then I'm going to show you this one. Okay? So now I'm actually going to do a query that is a lot more interesting than the ones that you were just talking about. So what I'm going to do is I'm going to go to the Yelp reviews, and I'm going to look at the text of the review, but I'm going to text of the review and represent it as a vector, like I've just shown you, right? So, like this one. So I'm going to represent it as a vector like this, and then I'm going to take a query, and my query is this complex query. It says, I want to find documents that have the word pizza and crust or sauce and the word delicious or tasty, right? So you could say it's horrible or, crust is horrible. Anyway, so the way that you do this is that you represent the query as if it was a table, and then you basically say that the vector representation intersects with the query. So this is a special operator for text queries. Then you can take the results and you can rank them by this function that finds relevance of the vector to the query. Now this is a very inefficient query because I am taking the review text and making it into a vector on the fly, right? In real life, you would actually do the conversion and store the vectors inside the database. But you can, in fact, run this query right now as is, even though that is not very efficient. It's connected to the Yelp database. Okay. So now it's ranked by, the reviews. So Depositious comes first as having a review that has these words, whereas Dante's Pizzeria and La Bella come as last. So do we think that Depositious is more tasty than La Belle's or Dante's? In any case, that is mentioned more here than here. So this is kind of the general idea. In fact, there are two Depositious reviews that have this property. So this is the general idea that I want to show you, that there's a whole world outside of just basic SQL, that things you can do by all of these extensions, and you can write the extensions yourself. Okay? I know this is a very long lecture, but I have one more thing to show, then I will be done. Okay? All right, so the one last thing that I want to do is show you this relation. This is also linked from the course notes. So we talked about the object-oriented version, that you have complex data types, and you can have methods that operate on those data types. So you can store things encapsulated as a point instead of two separate x and y values, and then you can have methods that operate on points. So this is something that we are very comfortable with from programming languages, right? And your methods are polymorphic, that they inherit, and you can have the same method defined for different inputs, and all of that cool stuff you know from programming languages. But you can also do something that you cannot do in programming languages. You can also have semantic inheritance. Remember when we were doing ER diagrams, that you can have the ISE, that a person, a faculty is a person, so the faculty inherits the attributes from the person, and the student is a person, so student inherits the attributes from the person, but student may have different attributes, and the faculty may have different attributes. So the same kind of deal exists. You can actually define that in SQL. So here's an example. I'm going to say that cities is a table that has name, population, and altitude. Okay? And I'm going to create a new table called capitals that has a state, but it will inherit all the attributes from cities as well. So if cities have a primary key, it will also inherit the primary key. So then I am going to basically create two separate tables, but this table is created to be under this table. Okay? So in fact, cities themselves have name, population, and altitude, but the capital has name, population, altitude, and a state. Right? These three are inherited, and the state is the additional. Okay? So, in my capitals, I only have New York. In my cities, that's interesting, because in my cities, I don't just have New York and Syracuse, but I also have Albany. So Albany is stored in this table. Cities store these two tables. But given that these capitals are under this, that means all cities include all capitals as well. But when I query the cities, I don't see, of course, the state, because cities don't have state, but it has the other three attributes. So this is an inheritance that is very different, right? It only inherits the attributes, it also inherits all the tuples. So the set of cities includes the set of regular cities and union the set of capitals. Capitals only includes the capitals. If you wanted to just return cities but not the capitals, you could actually, let me see, say this. that you want to return only cities that are not capitals, right? So don't inherit, just return only from that table. So you can actually create arbitrarily complex hierarchies, and then you can inherit that when you query. But what it happens is that anytime you write this query, there is an inherent union that happens, right? Because I'm actually storing them in two different tables, so it's unioning them. So to sum it up, databases, they start with the simple data model, and you can go very far. But over time, people have seen many different needs for more complex operations, so that they have actually implemented all of these object-oriented extensions that almost any modern database will actually have. It will be maybe slightly different, and there will be different versions, but you will actually have a lot more to explore once you get into it. As with everything, you have to use the tool for the thing it is designed for. Doesn't mean that you should throw away everything that you have learned, but it is, in fact, very useful for certain problems, so it is good to know. I'm going to stop right here, and then on Monday, I'm going to do a short lecture on object relational mapping. Then I'm going to do a review of SQL, so bring any questions that you have, and have a nice weekend.